Okay, so David, we just finished talking about what one-to-one and onto mean. Can you illustrate those definitions in an example?
Okay, so one-to-one and onto, why don't we illustrate it with a bijection, a function which is a bijection?
Yes.
So let's maybe remind everyone what a bijection is.
Yes.
So let's say, f is a bijection. And I'll maybe write a function.
Yeah.
Just to make it super clear. A function f is a bijection if it is one-to-one and onto.
Yes.
Okay, so let's come up with an example of a function that is both one-to-one and onto. So we'll draw a graph here. This will just be the, oh, that is not straight at all. That's more straight. Okay, so let's say this is x, and let's say this is f of x. And let's define function that's both one-to-one and onto. So f of x equals x cubed, which is this squiggly line here.
Yep.
Sorry, that should be 0. So let's go through this. And is this function a bijection? Okay, well, let's check the definition. It's a bijection if it is one-to-one. Okay, well, let's look at that. So is it one-to-one? Now remember, something is one-to-one if f of x being equal to f of y implies x equals y.
Right.
So let's say f of x is this. Well, to me it looks like, x needs to be equal to, we'll call that x star. To y star. So let's say y star.
Yeah.
Or f of x star, just to make it a little nicer. So there's only one point in the domain of this function, which is x, that maps to f of x star.
Yeah.
So if you've been given f of x star, or sorry, if you've been given f of, let's say, a, for example, and it's equal to f of x star.
Yeah.
Well, what can you tell about a?
There is no other value
Yes.
in x that can map to f of x star.
Right. So f of a, the a needs to be x star.
Yes, the a has to be x star. Yeah.
Okay. So I think we've got the one-to-one.
Yeah.
Is this function onto? What do you think?
Yes, because for every value in f of x, there is
in the image, right?
In the image,
function, yeah.
There is a value in x that maps to it.
Right.
Yes.
Right. And that's pretty easy to see, right? Like, let's say you had f of x equals 10,000. Well, you just find the cubed root of 10,000,
right? And
you've got your point in the domain of function that maps to 10,000 with this function.
Right.
So yeah.
Okay.
So it's one-to-one. It's onto. It's a bijection.
Okay. Good. So we just took that detour to talk about what a bijection is. Let's now go back to our original point, which is countability.
Yes.
So a set is countable if there exists a bijection between the natural numbers and that set.
Yes.
So let's apply that to the rational numbers.
Okay.
So is the set of rational numbers countable? So we need to show whether or not it is a bijection.
Well, yes. So remember, something's countable if there exists a bijection between the natural numbers and a set. So what we'll do, we'll use proof by construction.
Okay.
Which is basically, I want to prove something exists. I'll give you an example of it. It definitely exists if I can come up with an example.
Okay.
So,
but it has to be generalizable, right?
Yes. Yeah.
Right.
Well, in this case, right? Like
yes.
You're asking, does there exist some bijection? And something is countable if there exists a bijection between the natural numbers and the set, right?
Right.
So you just need one bijection.
Right.
If there's one, you've got it. You've proven it.
Right.
Okay. So why don't we create this bijection?
Okay.
So we need to create some sort of function between the natural numbers and the rational numbers, being the set, which is a bijection. So let's say there's a function between natural numbers and the rational numbers.
Right.
Okay, so I'm going to create a bit of a crazy function, but we're going to see that this function is actually a bijection.
Okay.
And we're going to create the bijection, and then it's going to be, well, the set's countable, because that's how you define it.
Right.
Now, I should point out here, right, that being countable, that doesn't have anything to do with being finite or anything else.
That's a good distinction to make. Right. Being countable is not the same thing as being finite or infinite.
Right, because as we're going to see here, the rational numbers, they're countable, but there's an infinite number of elements in them.
Right.
So let's clear that up. So here's what I'm going to do. I'm going to create this bijection by creating a mechanism where we'll basically create a list of all the rational numbers. And we'll see if we continue doing this at some point. We're going to hit every single rational number P over Q, where P over Q are in lowest terms.
Right.
So why don't we start with the middle rational number, let's say, was 0 over 1. So is equal to 0. Okay? And we're going to change the numerator and change the denominator, and you'll see we'll get all the rational numbers. So let's create a list. So 0 over 1, 1 over 1. Make sure to get the negative. So negative 1 over 1. Okay, 1 over 2. Negative 1 over 2. And let's do 2 over 2 and negative 2 over 2. And I'm just going to stop right here and say, we actually don't need these two numbers, because we can agree that 2 over 2, negative 2 over 2, it's equal to those numbers.
Yes.
So we're gonna do this mechanism, but each time we hit a rational number that we've already seen somewhere else, once it's put into lower terms, we're gonna discard it because we don't.
Okay.
However, we haven't seen 2 over 1, negative 2 over 1. Okay. So would you? Yeah, these are all the rational numbers where P or Q is equal to 1 or 2, basically. So when P and Q are the numbers 1 and the number 2, these are all the rational numbers.
And 0.
And 0.
Yes.
This is all. So let's keep doing this just for maybe another number, just so we see it. So 1 over 3, 2 over 3. I'm not going to write 3 over 3 there. Negative 1 over 3, negative 2 over 3.
Right.
So, okay, let's go back. So now we need 3 over 1. Over 1. Negative 3 over 1. And let's go 3 over 2. Negative 3 over 2. Okay.
So you are, in a systematic way, listing all of the possible rational numbers.
Yes.
You started off by doing it with just 0, 1, and 2, and you've now just done it for 0, 1, 2, and 3.
Right.
And if we had more time and more space on the whiteboard, we can do this for 0, 1, 2, 3, 4, 5, and it would just be a matter of enumerating all of those possibilities.
Exactly. And that's the beauty of this mechanism, is that if you keep enumerating in this fashion, eventually for each P over Q, where let's say P over Q are in lowest terms, you will reach that value eventually. It might take a long time. It might be the fifth number, but it might be the 10,000th number. You'll eventually hit it.
Right.
This is for a general P over Q.
Yes.
And the rational numbers, remember, it's P over Q being a fraction.
Yes.
That is the set of rational numbers. So we know that eventually we'll enumerate every single rational number in this way.
Yes. So earlier when I made the comment about generalizability, this was what I meant.
That's the generalization.
That's the generalization that we were talking about. Yes.
Right.
But you are correct that as long as you, sorry, as I often do, just going on tangents. If you just find one bijection to show that there is a bijection between the natural numbers and the rational numbers, then you've proven that the rational numbers are countable. Right. So suppose that David enumerated this with the negative numbers, with the negative number here and the positive number here. He would still be enumerating all of the rational numbers, but that would be a different order of the enumeration, and therefore it would technically be a different bijection.
Yeah, it's a different function, but it's a bijection nonetheless.
Right, and I think that the key thing that David mentioned earlier is, as long as you find one bijection between the natural numbers and the rational numbers, you will then prove that it is countable.
Right. It's kind of a low bar. You just need to prove there exists one.
Yes.
And then you've proved it's countable.
Yes. Very. Thank you for making that distinction.
So we've got the numbers kind of set up right here, and let's just I'll just keep keep the top row.
Okay.
And maybe just erase this just so it's and we'll add the general case here as we had
the P over Q.
Yeah. So P over Q.
Okay.
Okay. So we've got these rational numbers, numbers which are in the range of this function. Okay, so let's create the bijection. So this will be, I just don't have enough space, so this will be Q, and this I'm going to just move this over a little bit. So this is going to be f of x, and this will be 0 over 1, and then 1 over 1.
Right.
Okay, so that's these lines are pretty straight. that'll be the range of the function right there.
Yes.
And we'll just put that in here, and then okay, so I'm now going to create the domain of the function. So the domain of the function is the natural numbers. And we'll call this x, just to be perfectly clear. Okay, so we need to create some sort of bijection. We'll use the definition of the natural numbers where it doesn't include 0. Okay. Actually, let's make it include 0, just because 0 is in there. So let's do 0, 1, 2, 3, 4, 5, 6, ... So just be a general lowercase n.
Okay.
And we've created a bijection. It's kind of messy. It's kind of a crazy function, but it satisfies all the properties of bijection. Maybe we can go through what those properties were. So is it injective? Is it one-to-one? So remember, in order for something to be injective, let's just write this down. So f of x equals f of y implies implies x equals y.
Yes.
So let's look at this function here. Let's say f of x equals 1/2. So we go here. This is our range of the function. So f of x equals 1/2. And let's say f of y also equals 1/2. Well, what's x going to be?
It has to be 3.
It has to be 3.
Yeah.
Because will 1/2, the way we're creating this list of rational numbers, will 1/2 ever show up again?
No. It only shows up in this one and only one spot.
Right.
And the corresponding value in the natural numbers is 3 and only 3.
Right. Because remember, 2 over 4 will show up, but we're not going to include it.
Right.
That's not how the enumeration works.
Right.
So it looks like that's good. It looks like we got injectivity.
Right.
So surjectivity. And we've already almost talked about this in this part right here. This enumeration, this function, taking the natural numbers and the rational numbers, eventually you'll have P over Q for any value of P and any value of Q.
Yes.
And remember, we've defined the rational numbers as the set of all numbers, kind of 2 integers, P over Q, in a fractional form. So we know, just doing this, following this function, going from x from 0 to 1 to n, eventually we'll hit P over Q. It'll be in the range of the function for any value P or Q.
Right. So whatever P and Q are, this progression of the numerator and the denominator will eventually reach P and Q just by the growth of the integers.
Yes, the growth of the integers, either like P's, let's say P over Q is really large, well, the function will eventually get very large. Or if P over Q is something extremely small, well, maybe it's represented by like 1 over 100,000. Eventually, if you do this enumeration long enough, that number will show up. It's not a nice function. It's not a nice smooth, curve, but this function satisfies the conditions for a bijection.
Right. Okay, so it's not a rigorous proof in that we've written exactly why this is one-to-one or onto, but I think visually it's intuitive that it is the case. So I hope that this is an intuitive explanation for why the rational numbers are countable. Okay, all right. It does seem a little strange because rational numbers, we know they can have decimal values where it's infinite but repeatable. Where it's like I said earlier, it's 0.3333333, or if it's periodic, like 1 over 7, it's 0.142857, 142857. And when you see something that has a decimal expansion like that, it's hard to grasp that it's countable. But as this shows, rational numbers are countable.
It is a little counterintuitive, and the thing that's even more counterintuitive is, remember, we were talking about the rational and the irrational numbers, and you would think, okay, well, a irrational number is just a number that's not rational. Turns out irrational numbers are not countable, so you can actually do this with the irrational numbers, which is a little strange. You'd think you could, if you could do it with one set, you could do it with the other, but it's not the case.
You cannot do that. Okay, interesting. Well, this has been very educational for me. So we first talked about what some common types of numbers. We talked about the natural numbers, the integers, the rational numbers, the irrational numbers, and the real numbers.
Real numbers,
We then showed why the square root of 2 is an irrational number. We then talked about what countability is, and we went back to the more foundational definitions of bijection, one-to-one, and onto. And then based on that, we talked about why the rational numbers are countable. Okay, all right. That was a very nice summary. Thank you so much, David.
No problem.
To conclude, this is a question that I ask all of my guests. Is there a book or a website or a blog or a video or a course or something that you've encountered in math, science, or economics that you really like?
I actually read a recent book called Prediction Machines. The authors are 3 University of Toronto professors. They're at Rotman, which is the business school there. And it talks about machine learning, artificial intelligence, some of these, I guess, buzzwords that you hear a lot of. And it talks about what the impact on the economy and the impact on the world and the impact on business will be from these trends. And I find it very clear, very concise, and it talks about the big picture stuff, which sometimes these type of books might go into the weeds a little bit too much. So I highly recommend that book to anyone looking to learn more about that subject.
Excellent. And I'll make sure to put the name of that book and the author's names down below in the description of this video. Now, David, are there ways for people to look for you on the internet?
Yes. So I've got a Twitter account. So at Dave Veitch on Twitter, you can find me. And also I've got a WordPress website where I've got some projects that I've done and just some stuff I put up there. It's daveveitch.wordpress.com. You can find it there. And
I'll make sure to include the links to those in the description of this video. All right. Thank you, everyone, for watching this episode. I'm Eric Kai, the chemical statistician. If you'd like to learn more about statistics, chemistry, or career development, you can visit my blog, The Chemical Statistician. You can watch my YouTube tutorials on statistics or chemistry on my YouTube channel. You can find the other episodes of The Central Equilibrium on my YouTube channel. And of course, you can follow me on Twitter at ChemStatEric. If you have any comments or questions about this episode or any of the other episodes that we've had on the central equilibrium, please share them in the comments down below. Thank you so much for watching this video, and I hope that you learned something useful today.